We're gonna start off with an exciting talk by Jenny Green on the little red dots in Uncover.
All
right. Is it on? All right, very good. So this talk is going to be about bias towards the work that we've been doing in the Uncover field, but since I'm possibly the only observer here, I also want to be fair to all of the amazing work that has been going on with JWST at high redshift. You know, high redshift quasars is not my thing, so you know the data must be super amazing because I got totally dragged into this. All right, so this is the Uncover field. This is Abel 2744, so it's a Hubble Frontier field lensing field. And just to give you a sense, we have 7 near-cam bands with Uncover, 6 broadbands and 410 medium. And in all of the objects I'll be talking to you about today are bright by Uncover standards, which means they're like 27th magnitude. So it's just extraordinarily deep imaging data. And then in August of 2023, we also got near spec prism data for about 650 galaxies, including these AGN that I'm going to talk to you about today. So I want to give credit to the Uncover team because there's just a bunch of people who have done incredible infrastructure work, including Bingji Wang, who does the SPS modeling, John Weaver does the photometry, Adi Zitrin and Lucas Furtak do the lens models, and Sedona Price has been organizing the entire survey. Rachel Bazanson and Ivo Labe are the PIs. And like I said, it's just been incredibly fun. To introduce you to these specific AGN, this is our poster child. Lucas and I really wanted to call this Cerberus because it's a triply lensed source. Actually, 2 of these sources were known pre-JW, but with Uncover, we found the 3rd of these. And already you can see these are the photometric points that the SED was really quite strange. It's blue in the rest frame UV, it's at a redshift of 7, and quite red in the rest frame optical. And so we got really interested. It was challenging to model this SED, and what we proposed in the end is that we receive, oh, and I should say, it's lensed by about a factor of 7, and it's a point source. And so we can put a limit on the size of this thing of 30 parsecs, which already suggested that it was likely to be an AGN, although, you know, maybe it's stars. If it's an AGN, we thought maybe this was the intrinsic AGN component, heavily dust reddened AV of 2 to 4, something like this. Such things are seen in the universe. Eilat Glickman and Manda Banerjee have made their life to find these broadline AGNs that are reddened. And then there's also this blue component in the UV, which we proposed maybe was a scattered light component, just a few % of the intrinsic AGN light coming out in the UV. But of course, it may also be star formation. So that's the quick summary of these little red dots. And this was in 2022 that Lucas published the photometric discovery of this object. And then we got the prism spectra. We got spectra on all 3 images, 38 hours, which we say is something like 1,700 hours when you take the lensing into account. So this is the best that JWST can do. So I hope you're super impressed with this beautiful spectrum. One thing that is very clear, and even with the low resolution of the prism, which is about R of 400 at the red end for unresolved sources, unambiguously we see broad H beta. This is what the unresolved line would look like. And so we think this is pretty clear evidence that there's an accreting black hole in this system. We were not the only people to get interested in these so-called little red dots. That name was coined by Jorit Mathi and Rohan Naidu in their fresco paper. So this was GRISM data, which found all of these broad H alpha lines and really compact red sources. And then Rachel was also involved in these Sears papers, again, blue in the UV, steep red continua. Dale Kochevsky published this beautiful broad H alpha line, which incidentally, this was first published, one of these sources, as a universe breaker by Ivo, who said these were redshift 8, 10 to the 11 solar mass galaxies. So, you know, Ivo says he's playing both sides. They're AGN, he's right. They're big, massive galaxies, he's right. So anyway, that's the thing with the little red dots. Okay, So the next question is, how common are they? And that's when we sort of, well, actually one more slide on our data. So we, in June, we published a photometric sample of little red dot AGN candidates. And the basic idea is that we select very red things. So this is 277 minus 444. So we're just picking things with this really steep red continuum. And those could either be a 4,000 angstrom break, so very red, or this reddened AGN. The crosses are the things we now have spectra of, the prism spectra. So at least 30% of things that you select just based on this red color, especially if you exclude the things that are too red, because those are brown dwarfs. 30% or more of these are AGN spectroscopically confirmed by our prism data. So those are our broad lines. Taking out the 3 brown dwarfs that we got very deep spectra for, so 9 out of 12 are confirmed to have broad lines. If you further insist that they be consistent with point sources at JW resolution, particularly in the red where we have high signal to noise, then it's more like 80% of these things are confirmed to be AGN. So this gets back to Marta's point that there's a steep selection bias here. We really preferentially targeted things, but did not have extended galaxy components. They were consistent with point sources, you know, about 100 parsecs is the typical size limit we can put for the things that are just lensed by a factor of 1.5 or 2. So that's the summary of where we are with Uncover. And you know, I never thought we'd be this lucky, right? So we found a redshift 8.5 broadline AGN, among other things. So we'll look at that in a minute. This is a summary of the black hole masses. So they're moderate masses compared to UV selected quasars, and they're very UV faint. Again, we don't know even what that UV emission is. And then you see in the squares, these are the Maulino, the Harakane, and the fresco objects for context. So for instance, Maulino's jade sources are preferentially in bluer galaxies. We really targeted these red things, and ours are just a bit more luminous. So now, you know, I'm a rest frame optical person. I really want to get away from plotting things in UV luminosity, which like we don't know anything about it, and it's dusty, and so who the hell knows what's going on. But we can infer bolometric luminosities, but that's under the assumption that we're seeing a dusty reddened quasar, which intrinsically is just like all the UV selected quasars and just has an AV of 2 to 4. So if you make that assumption, then these are our little red dots from Uncover. So, you know, significant but moderate luminosity, 10 to the 8-ish solar mass black holes at redshifts of 5 to 7. And so I just want to present some of the properties of these and try to stay agnostic to the model, since that's your all's job. I think we're still trying to figure out which aspects of this is surprising and which things we still don't understand. So the first bit of context is, you know, this is the luminosity function, UV luminosity function for UV selected quasars. And what UV selected quasar luminosity functions do is they really flatten dramatically at low luminosity. And this is after, you know, extensive work by a lot of people to comb through lots and lots and lots of brown dwarfs to find which are the real quasars. And so what you see, these are the galaxies. So you see that the majority of galaxies are not harboring black holes if you think you're finding all of the accreting black holes with UV and X-ray. So these are the JWST new luminosity function. So now we're getting up to, with the little red dots, a few percent of the galaxy population, and with the broad H alpha selections more generally, 20% of the galaxy population. So from Maulino and Harakane. And then we go up to a little bit higher redshift. So this is our redshift 7 bin. And then through conversation with Marta, this is just a very preliminary comparison now. Bolometric luminosity functions, again, assuming that we understand the SED as compared to the CAT model. So it doesn't look like it's impossible to reproduce these number densities, but these are these super weird red things, and their number densities are pretty high. You know, we're already a few percent of the galaxy population. And you remember they were selected to be compact. So I'll show you that the black hole is a large fraction of the mass that we can see. So I keep saying we want to talk about things in bolometric luminosity, but I also want to really emphasize that we do not understand the SEDs. So here on the left was our attempt to model this red plus blue component with, this is the underlying vanilla Sloan quasar. Here it is, reddened by an AV of 2.5. Then we can add in either some star formation or a scattered light component that is only 2.5% of the underlying red thing. So those are basically our best models to date. But one thing that you would absolutely expect if this was a normal reddened broadline quasar is that as you go redder, the continuum should rise. It should be duck soup to detect these things in MIRI. And what Christina Williams has recently shown is that instead the SEDs completely flatten as you go to, rest frame mid-infrared. So that was a real bummer while we were trying to write JWST proposals. To know if we really know what the bolometric luminosities are. Maybe there's more galaxy light in this part of the SED than we thought. That's what Christina suggests. And at least in a couple of cases, we have very deep X-ray in the uncover field from Akos Bogdan, and our lensed friend, we think, is about a factor of 10 less luminous in the X-ray than we would expect, again, with this underlying model for the bolometric luminosity. So the last two things, are they overmassive? Is that interesting? So this is Vasily Kokharev's redshift 8.5 little red dot. It's a point source, so we put some sort of limit of 10 to the 9 solar masses on the stellar mass. This is Lucas's lensed friend. Again, we think the most mass you can fit in that 30 parsec radius is about 10 to the 9, and these are the black hole masses. Sort of naively, our observer expectation was that as you got to these more moderate luminosities, the black hole to galaxy ratio should approach closer to the local relation, but these things that we have admittedly selected to be AGN dominated are really lying quite high in black hole to galaxy ratio. So it's an ongoing question, I think, about how natural it is to explain these in the models. And that's just where generically the little red dots would fall. And then finally, the question of, is it hard to grow these? Most of our little red dots are redshift 5 to 7 and moderate black hole masses. So there's no time crunch per se, but this redshift 8.5 friend does appear challenging to grow if you do the typical start at 100 solar masses and grow at Eddington until redshift 8.5. And then, of course, I have to mention our favorite X-ray selected AGNs. This is at redshift 10. This came from Akos's X-ray uncover work. And then we followed up with a prism spectrum. So Andy Goulding led this paper confirming that it is at a redshift of 10, but rather devastatingly seeing no evidence of the AGN in the rest frame UV. So anyway, it's quite massive. Again, the inferred black hole to galaxy ratio is very high, and you have this challenge of how do you grow the black hole at redshift 10 so quickly. So I will just leave this as the summary of the properties of these little red dots. Their number densities are high. They're a few percent of the galaxy population at redshift 6. Their black hole masses are high by selection, but then we do have these high number densities to contend with, and at least some of them seem to push the limits of growing things with, you choose your seed mass. And then I guess one question I have for all of you is the interaction between growing the black hole early and not growing too many stars, and whether that proves a challenge for the models as well. And I will end there and take questions.
All right. Oh, Rachel's right in front of me.
Hey, thanks for a wonderful overview, Jenny. We've already had some muttering about what the real error bars should be on things like, this key plot on the left here. So do you want to talk maybe a little bit about how the black hole mass estimates are obtained and what you think the real error bars are, and possibly also touch on the stellar masses, although maybe people are more familiar with that?
Sure. So probably the most important and unconstrained assumption in the black hole mass is the same thing that I harped on throughout my talk, which is that we don't know the luminosity. So I think the line widths are well measured.
From line widths.
Yes, it's
Usually
these
H
single epic AGN masses that assume that the gas is virialized and that we can figure out the radius of the gas from the AGN luminosity. So that's all calibrated at redshift 0 and
How wrong could it be?
well, so if you just assume it's some fraction of Eddington, you won't get a very different answer, 10%, 20%, 30% Eddington. But I don't know the bolometric luminosity. I don't know how reddened it is. If I make this assumption that the underlying SED is just like a Sloan quasar, and then I need AV of 2 to 4, that is a huge bolometric correction. It is very uncertain. Until I can pin down some other wavelength where I can see the damn thing, which is not Miri and it's not X-ray, it's very hard for me to know what is the underlying SED. So I think that is the big uncertainty. Now, on the galaxy side, if Eric Bell were here, he'd say, well, in early days of HST, you said there were no we said there were no host galaxies, and then we looked harder, I mean, JWST is very sensitive. These things are point sources. But could there be a merger under there, low surface brightness? Could the galaxy be dustier and hiding? I mean, I think we still have some really obnoxious rabbit holes to go down. On the other hand, like, I don't think you can fit a few 10 to the 10 stellar mass there and me just not be able to see it at all, because we get to 29th magnitude and they're, So I will also say the thing that I have a student now staring at, I mean, all are a bunch of theorists, but look at this spectrum. There's a break. There's a break at 4,000 angstroms. Usually we call that a 4,000 angstrom break.
That was the original LaBey thing, right?
Right. So while there is broad lines and there are AGN here, I think, I mean, I don't know a way around 2,000 to 4,000 kilometer per second broad bomber lines. It does seem like we may be seeing galaxy light too. So we're going to sort this out, hopefully. All right. Sorry, that was a long-winded answer.
Yeah, sorry if these are very naive theory questions, but so the two questions are, do you sometimes find evidence of broad metal lines like O3 that could point to the presence of winds?
So I went very quickly here, but our prism spectra have abysmal spectral resolution. At the very red end, where we're seeing the rest frame optical, it's R of 400, which means that whether the line is 200, 300, 400, or 500 kilometers per second, I'm going to see the same thing. So we, if you're on the JWST tag, give us some time for higher spectral resolution data. But right now, we don't really know. The fresco observations are high resolution, but they don't have H beta. They only cover H alpha at redshift 5. So that's what we got there.
Right, and just the very quickly, the second question is, so the Lyman alpha line, so I'm not sure I can judge this correctly. It looks narrow.
Again,
it's the same answer.
The resolution there is 20 to 30.
Okay.
So the Lyman alpha lines are probably not 3,000 kilometers per second. We haven't touched the Lyman alpha yet. If someone wants to tell me what the hell to do with it, I mean, but yeah, we detect them 60% of the time. We detect them in Lyman alpha.
Just a quick question. Have you stacked the little red dots to try and see if you have the stellar emission?
We haven't stacked them. I mean, this thing is extraordinary signal to noise because of and the spectral resolution is so different.
The photometry, like, have you stacked the?
Oh, just stack the photometry.
Yeah, you might be able to detect this if there is stellar continuum.
That's interesting. The other data thing that just happened is that Ren Sua
mega science data dropped from JWST. So we have all the medium bands in NearCam. So we're going to have some very, very deep, incredible wavelength coverage for all these things. So I'm not sure stacking is going to be the right approach because we're so deep. But we are really working hard to do the joint modeling of the galaxy and the AGN right now.
All right, I think we're gonna have to leave it there, but please thank Jenny again and find her at lunch.
I can use this too. That's fine. Okay, so. Okay, I want to thank the speaker or all the committee members for inviting me here to talk. I also want to thank Jenny for showing some spectra because I'm going to show you a lot of emission lines. A lot of people have asked me where Elon University is located. So I'll give you a hint. When these two teams play in basketball, we prevent them from fighting one another. So we are right in between UNC Chapel Hill and Duke University, and we are a primarily undergraduate institution. Which means that I work with exclusively undergrads and graduate students at other institutions. And so a lot of the work you're going to see today is enabled by them, and that's something that I'm particularly proud of. So I'm going to speak about dwarf AGN. So why should we detect them? So while we would love to do this comprehensive JWST survey at high redshift to detect all the black holes and all the galaxies, that's likely going to be cost prohibitive. And so another backup is to look at local AGN, okay, and dwarf AGN. They can set a limit to the occupation fraction, so a lower limit to the occupation fraction, and that can help constrain black hole seeding mechanisms, whether you have heavy seeds or low seeds. And if we want to find dwarf AGN, we can't use traditional methods for finding giant AGN. So one reason is that black holes or IMBHs wander about a kiloparsec off center. So you really need IFU spectroscopy to detect them. And also they have a wide range of morphologies. So dwarf galaxies can be elliptical, they can be spheroidal, they can have spiral structure, and so forth. And something that hasn't been accounted for in photoionization modeling a whole lot are these geometries. So what we sought out is to use different ways to mix the AGN spectrum and the starlight spectrum, and using plane parallel slabs or spherical geometries to see the consequences on the emission line output. Now, when you do so, a common emission line ratio that you might be familiar with in the optical is O3 over H beta. And you can see this has profound effects on the emission line predictions. The thickness in the line is due to a difference in geometry, and the difference in the colors is due to how you're mixing the spectrum of light with starlight versus AGN. And so you can get about an order of magnitude difference in the emission line predictions based off of this. Another factor is using we don't know the IMBH SED either. So you can use two different models that assume the same black hole mass. So here we're assuming a black hole mass of 10 to the 3, and you can get vastly different X-ray predictions and predictions for where the accretion disk lies. And so then the plot on the left now just becomes an absolute combobulated mess that you can't really decipher AGN fraction because there's so many different uncertainties to geometry and mixing methodology. If you want to find AGN using the BPT, it's hopeless, dwarf AGN, because they all lie in the star-forming wing of the diagram. And the reason is because this is a metallicity sensitive ratio. And so all the dwarf AGN are going to be detected as star-forming galaxies. Now, there are other diagnostics in the optical, which are much better for finding these dwarf AGN. For example, the O1 line at 6300, which is on the far right there, is relatively metallicity insensitive, and you can detect an AGN fraction of around 8% or higher. And so we had a PhD student who was working on this in a local survey of Z=0 dwarf galaxies to find these AGN using the O1 line. And so we found a unique type of dwarf AGN. It's called star-forming AGN. So they're in the star-forming wing of the BPT diagram, and they're in the AGN part of the O1 diagram. And so we find that most dwarf AGN are star-forming AGN. They're highly star-forming and metal-poor and gas-rich. And in doing so, we come up with estimates that the AGN fraction for dwarfs as equals 0 is around 15%, which is around 15 times what has been found through other optical surveys. And if you use the black hole mass, stellar mass relationship, whichever one you want to pick, basically this comes out to black hole masses that are ranging anywhere from 10 to the 3 to 10 to the 5 solar masses. Okay. Now there is a problem with using 6300 over H alpha. And one is that it's going to limit your sample size quite a bit. And the other is that it's going to not detect AGN at very low metallicities. And that's not to say that the O1 line itself is not useful for detecting AGN fraction. It's just that this diagram that we typically use has been calibrated for massive AGN. Okay, so there are other options in the optical. One of them is the helium-2 line with 4686 over H beta. And so it's relatively insensitive to metallicity and traces AGN fraction relatively well. One of the difficulties with helium-2 over H beta is that you can have contaminants from HMXBs, so high mass X-ray binaries. So I've been working with Kristen Galifari at NASA. And so what she has been working on is finding ways to self-consistently include high-mass X-ray binaries into photoionization models and stellar population synthesis as a function of time and as a function of metallicity. And so in the grids here, you can see the solid lines are, the solid grids are from high-mass X-ray binaries, and then the grids that have the dashed lines are from the IMBHs, and each panel is showing a different AGN fraction. And so when you get to around 8% or above, then you start to distinguish IMBHs from HMXBs. And so this diagram is potentially useful for defining sort of different regions where you can find stars versus HMXBs or IMBHs. You can come up with this sort of tricolor flag here where the BPAS, so just Wolf-Rayets are in the green. You have HMXBs or IMBHs with low AGN fractions in the orange. And then in the blue, you have strictly IMBHs with larger AGN fractions. However, using O1 and using helium-2 doesn't give us a full picture because they both have their limitations. They're valid in different metallicity regimes. And what we would ideally like to do is go even lower than 16% AGN fraction in order to detect IMBHs in these really highly star-forming dwarfs. Okay, and so I'd love to tell you that JWST is here to save the day. And in fact, it actually is. But we have to use MIRI, and it's been scandalously underused, so let's use it. And so with MIRI, what we can use is the O4 line at 25.9 microns and also sulfur 4 at 10 microns, and we can see really great distinctions between HMXB excitation and IMBHs. And so we have a number of proposals and to follow up on these local dwarfs and be able to decipher between the two excitation mechanisms. Now, some current limitations, there's tons of limitations in photoionization modeling, but one of them is that we just classify galaxies as either AGN or star forming, when really it's a continuum and you can have various AGN fractions, and we really need to think about it in a probabilistic way rather than just having these binary classifications of is it in this part of this diagram or is it not, right? Which means we need to get Bayesian with this and also incorporating complex mixing and ISM geometries into this modeling as well. So this is what we've been working on most recently. To give you an idea what we mean by complex ISM geometries, it is, so for an example, here's a cartoon. When you use a photoionization model and you assume you have a single ionization parameter, density and metallicity, essentially what you're assuming is that all of the H2 regions in a galaxy are the same size. And if you ever look at a given galaxy, you realize that this is completely bogus. Okay, so this is not the way that you should be modeling galaxies. They're much more complex. So you can use multiple H2 regions. You can use a 2-component model and mix them in various proportions. But even better is using statistical distributions. You can use a power law of H2 regions. And then your line luminosity is just going to be a weighted integral over all of those H2 regions to then give you the predicted line luminosities. And you don't have to stop here. You can go and use different ages for your stars, and you could use different densities for your stars, and then you can use different metallicities as well, right? And then you could zoom in even more. And if you want to zoom in on the center, then you can put an AGN in there. And then the AGN is going to have different clouds, and those are going to have distributions. And you're probably thinking to yourself, how do you explore this vast parameter space and do it in an efficient way? So the answer is a code that's been developed known as multigrease. And so the developers are Beignet Laboutier and Lise Rambussen up at the top here, if you want to scan their code. And so this is a Bayesian code that is specifically designed to infer these statistical distributions from unresolved observations, like you would likely have at high redshift with JWST. So you give it a photoionization model, and then you can predict, you can compare to metallicity, star formation rates, detected lines, and you can infer the statistical distributions on the fly. So they don't need to be built into the photoionization model, but you can infer those. And something we would like to do is something the reverse with models and cosmological models is predict these distributions and have those inform the priors on our photoionization models as well. So that's something for theorists that we're really interested in using. So let's see what we found for an example in dwarf galaxies with star forming, but we've also done this with AGN, limiting a strong line sample. We find that overall the topological models uniformly fit our observations much better than the single cloud models. And that's not just because that we're using more free parameters. In fact, we're not overfitting the data. Actually, we're underfitting the data. And that's one of the great things about Bayesian analysis. If you just include more free parameters, your PDF just gets fatter and fatter. And so we can look at some of these, and there's a number of different metrics, likelihoods and marginalized likelihoods, predictive p-values that are showing that the topological models are doing better. Here's some of the early results that we're getting from star forming in AGN, the different PDFs. So here is metallicity and ionization parameter and age. What's really neat, the slopes on the statistical distributions, we just use power laws. We're not tied to those. We just use them because everything's a power law in astronomy, but you could use Gaussians or you could use chaotic fractals, whatever you like. And then, so here are the different metallicity distributions. What's really neat is that the code wants to use distributions, right? We're not telling it to do so. If a single cloud model was better at reproducing the data, then the boundaries would just lie on top of one another. It's also neat that you need to get ages that go up to the Wolf-Rayet stage, okay? And so you're getting really bursty young stars, but then also these Wolf-Rayets in order to reproduce the emission lines. We can look at star formation as well, and something we want to do is eventually tie this to AGN activity. You can look at the evolution of the boundaries. So the top bound or the upper limit boundary is given on the top in red, and the lower limit boundary is given in blue. And that's as a function of the statistical average of the distribution, which you can think of roughly as the average metallicity or the stellar mass. And you can see that the evolution of the boundaries, they occur at different rates, and inferring that there might be some critical threshold for star formation. And once you get at a certain point, then the star formation takes off. We do see that the boundary in between, the distance in between the upper boundary and the lower boundaries closes as a function, or it widens as a function of metallicity. And that's something that we see in these radial gradients of metallicities in galaxies like in Manga and in SAMI. So what we'd like to do is then also add AGN onto this to figure out if it's suppressing star formation and maybe color code it according to the AGN fraction. So future work, just to briefly preview it, we want to do statistical distributions, look at models, so theory, figuring out the distributions to inform our priors, but also at SAMI and Manga, the observations. So we would love to use this for high Z observations of JWST, which are going to be unresolved, to disentangle those topological distributions, following stochastic accretion as a function of cosmic time, and figuring out what the heck is going on with IMBH SEDs. Okay, right, thank you.
Questions for Chris?
Super cool. I'm wondering about the constraint of Sloan, Sammy, Manga just being pretty incomplete below stellar masses, below LMC in terms of spectroscopic volume that they probe and stuff. So I wonder, I mean, JWST is one question, but just in terms of multi-object spectroscopy, like, is DESI going to be good enough? You know, what's your ideal data set?
Yeah, I'm not sure on that ideal with Manga and Sammy. I mean, definitely incomplete. We're trying to get an idea of what the distributions look like. I mean, we're assuming a power law. It could be Gaussian, it could be anything. We did some early work just kind of looking at, and they mostly turned out to be these they're like these cutoff power laws, something until we dug into the data, we didn't know. We just had a power law with rough cutoffs. And then when we looked at the Manga data, then we're like, oh, they trail off, which they should, because there shouldn't be a hard cut, right? And so that improved our fit quite a bit, even though it introduces more free parameters. So I think first order is just figuring out what it looks like, even if they're in higher mass galaxies, and then we can start thinking about like ideal data sets to push it into like the dwarf regime.
Okay, thanks.
Yep.
Any other questions?
Have you tried comparing your AGN fraction, your observed AGN fraction with cosmological models? Because I'm guessing there's only a very limited range that would ever get to 15%, as Melanie showed earlier in her talk, even though, yeah, they span a vast order of magnitude. It's spanning it towards the lower end. So do you think you can maybe even derive constraints on AGN accretion and feedback models from this high fraction?
That's something that we're interested in. I was actually talking with Melody at the break about this and how we could take those types of simulations and turn it into something that would be observable, you know, and so we're always assuming, like at least in our models, that the AGN is accreting at 1% at Eddington, and it's not. It's it's very stochastic in its accretion. But I think these local samples, the sample that I'm using here is truly volume limited, so it has a really low mass floor. And so I think that if you're predicting those and you're really good in getting AGN fractions in there, that's at least comparable to what you're seeing from the simulations, as opposed to SCSS, which is going to be flex limited and you're only going to have the giant AGN. So I think there's hope, but I definitely want to figure out ways to make them directly comparable with one another.
Okay, great. Let's thank Chris again.
Yeah. Okay. Hi, everybody. I would like to thank the organizers for such a fantastic conference. It's amazing to be able to synthesize research from so many different aspects of the same question. So my name is, if you're Indian, my name is Urmila. If you're not, you can call me Mila Chademuri. I'm a postdoctoral fellow at the Max Planck Institute for Astronomy. That's the one in Heidelberg. But the work I'm presenting today, I did largely while I was at the CFA. And so much of the groundwork has been laid by speakers before me, so thank you very much. The essential question is, how can we test different models of the seeding and growth of supermassive black hole seeds by using observations of dwarf galaxies in the local universe? So just as we know at this point, we have many, maybe too many ideas of how these supermassive black holes can form and grow over time. And these different models produce different, have different predictions for what we call the black hole occupation fraction, okay? Which can be a function of any number of things. But in general, we can talk about it in terms of something like the stellar mass of the host galaxy, as well as redshift. Now, you have various ideas for what the seed models are, right? They could be light seeds like population 3 stars. They could have intermediate masses all the way to heavier seeds like direct collapse black holes. And these could then also grow through a variety of different channels. We don't know if the growth is predominantly sub-Eddington or super-Eddington, and to what extent mergers affect the growth rate, right? And so it's this combination of different seed plus growth models that result in a certain occupation fraction, which is a function of the stellar mass as well as the redshift. Now, if you were to look at very high redshifts, the way that we can do now with JWST, you know, the growth is a subdominant component, is a relatively subdominant component of what you observe, right? So you're sort of more, not directly, but more directly observing the different seed models. But as we know, these observations are extremely biased, and there's so much we also don't know about how to measure the actual black hole masses and even the stellar masses of the galaxies. So while it is important, it is also great to combine this, to complement this with studies in the local universe, where suddenly the growth becomes very important because these things have been growing for 13 billion years or longer. Right? But on the other hand, we have a better chance at having a statistically representative sample and understanding a lot of the observational systematics, and we sort of know better what we're seeing. So the question is, can we indeed discern between the effects of different growth channels and different seed models by looking at the local supermassive black hole population? So the approach that we're using is based on semi-analytic models. Specifically, the ones that I worked with were all developed by Angelo Riccardi right here in this room. And the basic summary is that you start with halo merger trees that are Monte Carlo merger trees. So you have a population of halos going all the way back up to high redshift. Then at each redshift, you use a variety of scaling relations to populate the dark matter halos, first with a stellar mass, and then with a galaxy size. And then those two together give you a central velocity dispersion sigma. And then, you know, that sigma is then converted into a black hole mass. So this is how you end up with this catalog of halo, stellar mass, and black hole mass properties over a large spread in cosmic time. Now, the big advantage of SAMs is that they are computationally very efficient, and so you can run both many iterations to account for things like cosmic variance, and also you can implement many different models. And so specifically in this study, I looked at Angelo's models where you could start with either a light or a heavy population of seeds. And then for each scenario, you could grow them in 3 different ways. And so these all represent just different ideas about how these black holes grow. So the black holes can grow either by mergers or through secular accretion. And so the way that mergers operate is that if 2 halos merge, there's a 10% chance that the supermassive black holes merge as well. Okay, so this is accounting for in spiral times and dynamical friction. And so now if the black holes don't merge, then you can assume different ideas for what their Eddington ratio distributions would look like. And so in one popular observationally as well as physically motivated idea is a power law, especially when you look at radio observations of Eddington distributions, they seem to follow a power law. There's also this idea that the AGN activity closely traces the star formation rate. And so that's the AGN main sequence model. So you compute the star formation main sequence rate and then assume that the black hole accretion rate is just a fixed fraction of that. So that's the AGN main sequence model. In other words, black hole growth is proportional to the star formation rate. And lastly, you have this broadline quasar model, which was empirically motivated to reproduce the BLQ luminosity function at high redshifts. And so here what you assume is that so the black holes actually only grow in this model if their halos are merging, right? So I told you that if the two halos merge, there's 10% chance that the black holes merge. But in this particular model, even if the black holes don't merge, the moments where the halos merge are the only times when the black holes themselves are growing. So essentially, it's like assuming that this is the moment when a lot of gas is funneled into the central regions and powers these like bursty modes of growth. And those accretion rates are drawn from the broadline quasar luminosity function as a function of redshift. So by construction, this reproduces the quasar luminosity function at high redshift. But we're going to test it at low redshift. Right? And so these different models will produce very different predictions for what the X-ray luminosity of these AGN will look like as a function of stellar mass at redshift 0, right? I'm showing you here the light seed models on the top, the heavy seed models at the bottom, and then the different columns represent the different growth channels. And as you may expect, the first thing that you notice is that the growth channel seems to have a much more dramatic effect than the seed model just by eye, right? Which again, this is what we expect. But there are certainly differences between the light and heavy seeds. So how do we actually quantify this? We want to compare this to observations. And so we are going to use a Bayesian approach over here. We're going to, we want to be very careful about what observations do we have, what are the uncertainties, what are the limits, and then how do we compare that to our SAMs. It was mentioned earlier this week that SAMs notoriously underpredict the scatter in a lot of our observed scaling relations. And indeed, the first thing that you might see here, right, is that most of these models, especially the AGN main sequence model, has far less scatter than the observations. And so the first thing that so the first thing that I do is I just add enough scatter to the SAMs so that the detected fraction of AGN in the SAM mock catalog matches that of the observations. So this way, the model is still self-consistent because I'm not like forcing all the black holes to be more or less luminous. I'm just adding stochasticity to how often they might be accreting at a given rate. So over cosmic time, everything is still self-consistent, but then you can say at redshift 0, you would still match the observed active fraction. Second, as again was also noted, observations are flux limited. And if you were to only compare the active fraction, right, your conclusions are very sensitive to your flux limit, right? And so here you will see that all the light seed models I show as dotted lines and all the heavy seed models I show as solid lines, and then the different colors are different growth channels. And you see that even if you have a flux limit of like 10 to the 38 ergs per second, which was the resolution of Elena Gallo et al.'s AMUSE survey, which is still some of the state of the art in the field, it's really, really difficult to tell between light and heavy seed models. And in fact, like when I started out this study, my hope had been that I could improve on existing constraints by just using a shallow but very deep survey, which was eROSITA at the time, right? And basically this plot told me that I was not going to be able to do that, yeah. And so, okay, so here we are. We have our SAMs. We are dealing with observations that have a flux limit. In this case, it was 10 to the 38 ergs per second. That's the middle panel. And so now what do we do? How do we infer the black hole occupation fraction, not the AGN occupation fraction, but the black hole occupation fraction from these observations? And so you use this Bayesian framework, right, where you add more parameters and you add more, you broaden your posterior as a result, but it's a more honest representation of what you know. So in order to detect an AGN, there are a few steps involved. First of all, is there a black hole in your galaxy? If no, no detection. If yes, is the black hole on? What is your AGN duty cycle? If no, no detection. If yes, then is your detection above the detection limit? And so this is sort of the pathway that you have. And so I'm just going to jump through to the results. But essentially in the black line and the gray bars show the the constraints from the AMUSE survey, which is this flux limited sample. Again, I will remind you with a lot of dwarf galaxies. And what you quickly see is that we can safely rule out models where it's all light seeds because they simply produce too high occupation fractions at low stellar masses, even with our like fairly generous uncertainties. And second, it looks like merger-driven growth, right? The blue lines at the bottom are not, that's not sufficient to explain the black hole population at low redshift. So we're favoring we're favoring heavy seeds strongly over light seeds, and we know that mergers cannot be the major growth channel down to low redshifts. And lastly, you can say, okay, so in this previous plot, there are two different growth channels, the power law distribution, as well as the one where it's related to the star formation rate, that both fit very well within the observed posteriors. And indeed, you can distinguish them by looking at, interestingly enough, the bright end of the luminosity function, which is very nice because that's not the hardest thing to observe. And and it turns out that actually like the observations are more consistent with a power law Eddington ratio distribution than something that is like instantaneously tied to the star formation rate. So yeah, so essentially this is a little exercise that I hope, oh, sorry. One more very important thing to note. This is a quick note. People asked about what sort of survey you would want to ideally tell these models apart. And this is just really hammering in the point that the depth of the survey really matters. And so here I ran a test where I created idealized catalogs where I knew the true occupation fraction and I knew the M star X-ray luminosity scaling relation perfectly. And from those mock catalogs, I applied the same Bayesian inference pipeline to recover the occupation fraction. And long story short, you know, the correct answers are, you know, this blue vertical line for the blue curve, the orange vertical line for the orange curve, and so on. And essentially, it's always easier to rule out low occupation fraction than a high occupation fraction because of this uncertainty about whether is there no black hole or is it just below the detection limit. And secondly, that you really want to push for smaller volume, but higher completeness and deeper surveys if you want to tell these different models apart. And in particular, actually, it was amazing to see Chris's talk right before this, because I think like Resolve is, for example, a very fantastic place to do this. And more surveys like this that are just really complete in stellar mass so that we're aware of all the uncertainties and the selection function. And then we can just focus on the uncertainties in the black hole seeding and growth models. Those are really the way to go in the future. So would love to see more of that. Thank you for your time.
Thank you. This is really lovely. I like how you compared observations with mock observations in a reasonable way. I have one main question, if there is time, another one. But can you explain a little bit how you add scatter? So you add scatter in the relationship between X-ray luminosity and black hole mass. Is this correct?
Yeah.
Okay. And so how that translate into other observables. So in the case of added scatter to the black hole mass stellar mass relationship, I know how that translates into other observables. I mean, Rachel, I think, wrote one of the very nice paper on this early on. But I don't really know how adding scatter to this relationship translates into, say, the luminosity functions also at other bands rather than only the X-rays.
Yeah, so the question that you've hit at here is what have we assumed about the SED? And we have basically assumed that we have assumed that the X-ray luminosity is just the bolometric luminosity times a constant bolometric correction. And I will grant that that is a large assumption. And so if there are better models for how the bolometric luminosity can be converted to luminosities in various observable bands, that will significantly improve our predictions.
You basically add scatter to L-bol, and then you convert that.
I add scatter to L-bol.
Okay.
And then apply a bolometric correction.
So I think that
Thank you.
is still.
Yeah.
But so have you checked the luminosity? the resulting luminosity functions.
Have I checked the results on the luminosity functions? So for example, yeah, in this, is there a better way to get to the end of this? So you mean, for example, this kind of luminosity function, how, yeah, adding,
Oh, sorry, for instance, in the UV. So if you add scatter to L vol,
yeah,
you do it mid-phase, but you have also consequences in UV or P or whatever.
yeah, I'm afraid I have not looked at that. Also at this point, as I said, it's just a constant bolometric correction. So yeah.
Okay, I think in the interest of lunch, we probably have to stop the questions there and move on to the next speaker. Fine meal at lunchtime.
Yeah.
The arrows.
Okay, but not this.
Let's see.
No advance on that.
Oh, yeah.
Okay.
Might have to use the arrows.
Okay.
Hello?
If you're standing there, you also don't need that mic at all. Yeah.
Okay.
Yeah, we can
Can you hear me well?
Don't let those two get too close to each
Yeah.
other. Horrible.
Because otherwise I will take it. Okay, hello. First of all, thank you to the organizer for giving me this opportunity. And I'm Elena. I'm a third PhD student. I'm doing my thesis with Arianna Di Cintio and Rob Grant in the ISC in Canary Islands. So today I'm going to talk a bit about what I'm doing in my thesis about the effect of the AGN in the zooming dwarf galaxy. And I want to start introducing this so popular in this Congress, stellar to halo mass relation. And you can see in both cases the relation that the relation that we can find between the stellar mass and its halo. And I don't have the, well, in both cases, in the red line, we can see the theoretical relation that we should have. But the reality is that the observation finds a lack into the low mass and the massive range. So as in order to explain that, as Brian told us yesterday, there is two kind of main processes that reduce the star formation. So in the low mass range, we have the supernova feedback, putting energy in the dwarf and spreading the gas away from the galaxy, and that way reducing the star formation. And in most massive range, the supernova feedback is not efficient enough to reduce the star formation, and we need the AGN feedback to quench the galaxy. So, however, the recent observational studies have found that the AGN could also play an important role in dwarf galaxy, and the fraction of dwarf galaxy hosting AGN could be larger than previously expected. So in this regard, there have been also some theoretical studies that have also found that the AGN could have a relevance also in dwarf, and could also be influence the star formation rate in dwarf. So I didn't put all the theoretical studies, sorry for that. But here we can see how, as Tiago told us yesterday, even if they found that the AGN play a role in dwarf, this behavior is still really sensitive to the modeling of the AGN that they use. So to increase the chaos, I used another module to this theoretical framework, and I used the Aurigal project. So these are zooming simulation, a set of zooming simulation with a galaxy formation model that includes ionization, primordial metal, line cooling, magnetic field, and which is important for us, black hole growth and AGN feedback. So
in order to study how AGN could affect the dwarf galaxy, what I do is that I run a set of 12 initial conditions, but every initial condition of dwarf have run twice. One with the whole galaxy formation model, which include AGN, and once without the presence of the black hole. So that way we can isolate the effect of the AGN in each galaxy. So if we first take a look into the sample that the fiducial sample, the one that hosts AGN, we can see how how they follow quite well the pattern regarding with the mass of the black hole, as the stellar to halo mass, as the black hole stellar mass relation, or the black hole sigma relation, in which the sigma have been measured in half of the effective radius. So, well, in each case, the square are my sample, and it's the color and numbered by the mass of the black hole. This is gonna be through the whole presentation. So, in order to measure how the agent can impact to the galaxy, we want to look for signal that the black hole are quenching the galaxy somehow. So if we compare our fiducial configuration with its counterpart, the one that was evolved without the black hole, here we can see how each point, the color point, the one that was run with the AGN, is linked to their counterpart, the one that evolved without the black hole. So we can see here the stellar to halo mass relation again, and the relation between the neutral hydrogen and their stellar mass. So in every galaxy, we can see how we have really less amount of neutral hydrogen for the AGN configuration, and also less amount of stellar mass. Looking that, we can induce that the AGN can reduce the amount of star-forming gas, and that can lead to the less stellar mass. So now, if we take a look into the star formation history of this galaxy, I don't have time to put all the galaxies, so I just choose the one with the smallest black hole, the yellow 11, and the one with the largest one. So in blue, we have the configuration with the AGN, green, the configuration without AGN, and I also show in dark the mass accretion history of the black hole. So you can see when the black hole born, the star formation history between configurations start to change, but it's clear that when we have the galaxy with the smallest black hole, the change is not noticeable. But we have a really huge reduction in the star formation history for the one that hosts the massive black hole. So we can think about having a correlation between the reduction in the star formation history and the mass that the mass of the black hole that the galaxy have. So to measure that the gap between the star formation history and configuration, what we do is that we took the ratio between the average star formation rate through the time for the AGN configuration and the no AGN configuration. And if we look into the relation with the mass of the black hole, we can see how the relation is not strong, but instead of looking to the relation with the black hole, we look into the relation with the ratio between the black hole and the stellar mass of the galaxy. We can see how the relation strong correlate with the discrepancy between the star formation history. And those galaxies that have a larger ratio black hole stellar mass have bigger discrepancy in their star formation rates histories, is the star formation history, and that means that they have the AGN is having more impact into the galaxy. We also look into some baryonic properties. Here we have the baryonic Tully-Fish relation. We can see here that the configuration with the AGN much better some previously studies that the configuration without the AGN. And we can induce here that the AGN is needed in dwarf galaxy to match the baryonic-terrific relation. And if now we look into the gas, if we remember, I say before that the neutral hydrogen amount, the total neutral hydrogen amount was reduced in the AGN configuration. And here, if we look into the total mass of the gas, which is the solid line, the dotted line is neutral hydrogen, we can see how the total gas follow more or less a similar distribution over the radio and end with a similar amount of gas in its configuration for its configuration. So here we can think that what AGN is doing is warming up the gas and not expelling the gas away from the center. So it's reducing the star formation gas, just warming up. And that way we can end with more or less the same amount of total gas, but way less amount of neutral hydrogen. And to end, I want to show you the dark matter density profile of the galaxy with the hosting, with the galaxy hosting the largest, the two largest black hole. I have to say that I didn't found like noticeable differences for the other galaxy outside the softening length. But for this galaxy, we can see how the dark matter density profile reduced in the inner part of the profile, and even can reach up to the 65% of the reduction. So yeah, so far this is what I wanted to say. You will see this all of these results published hopefully soon. And if you want to ask or just go to lunch, just let me know. Thank you.
I think we probably have time for one question, or if you're all really hungry.
Thanks very much for your talk. So correct me if I'm wrong, I think in Norriga there's a two-mode feedback model. So
Yes.
there's this heating of the halo and there's this central energy.
Yes.
injection. Which one is operating here?
Yeah, here the important one is the quasar mode, the one that is hitting the gas around, because the radio mode is just important for the massive halos. So I look into that, and the radio mode is not doing nothing in this practically. Even it's active because the both modes is always active, but it's not important in this case.